Today I'm presenting on probabilistic service life modeling implemented through WJE CASLE. So WJE CASLE is our in-house modeling software. CASLE stands for Corrosion Assessment and Service Life Evaluation. So the model was built in-house by a materials engineer. I was involved in the development of this model as well as some of the people in our audience here. And being developed in-house, it gives us full control over the process. So we can customize how the model is handling some of the input parameter based on the specific condition and circumstances unique to each project. And this is one of the important aspects of our tool because this makes it lots of time appropriate for handling unique situations. We also use probabilistic modeling, so we recognize that the inherent variability with concrete construction and concrete material, and for that we use probabilistic modeling approach. We used our model for modeling both existing and new structures, different types of structures, and we validated our approach using data that was collected from actual field investigations. So our model is started with investigations of existing structures. So we developed it and adapted it per project needs. So we kept adding to the capabilities of our model as we come across new challenges on our project. We looked at different types of structures, and most importantly, we continue to refine our knowledge based on what we learn every day from hands-on field investigation on existing structure to inform the durability design of new construction. And this included work on bridge decks, airport, power plants, and industrial ports. We use a customizable approach. So our model, we can consider cracking of concrete, for example. We can consider some protective measures like sealers and coating. We can also consider changing exposure with time. And we can model multi-layer systems, so we can model concrete overlays. We also have experience based on lab testing and field investigation on polymer overlays, so we can also consider that in our model. So in thin polymer overlays or pre-mixed polymer concrete overlay. So in addition to all the information on what we learned from numerous field investigations, our model also is founded based on approaches and methodology available in the literature. So mainly Fib Bulletin 34. We also have in some of the input parameters, we handle it similar to what is described in Concrete Society Technical Report number 61. We also refer to the documents developed by the 365 committee here in ACI, and also the Life 365 technical manual that Mark described earlier. And this is, of course, in addition to other sources in the literature and research papers. So we can model new and existing structures. However, those are handled a little bit differently. So for new structures, what we model is what is the probability of exceeding service life limit versus time. So here we have the limit of 10% probability of initiation. So we're looking at probability of exceeding that threshold, which is the initiation of corrosion. The working with new structures, it involves making some assumptions. So, for example, concrete cover, we assume distributions based on construction tolerances because we don't know yet what is the as-built conditions. Sometimes we also assume different types of rebars, and based on the results, we can decide which type of rebar would be appropriate to achieve the service life requirement. We make assumptions to exposure as well. And we test concrete performance to inform our model. For existing structure, on the other hand, we model what is the percentage of corrosion-related damage and how that increases with time. And we rely on our input parameter on the field investigation. So typically we collect the core samples, we look at chloride profiles, and based on that, we can define our concrete properties and exposure conditions. We do GPR survey, and based on that, we define our cover distribution. And we verify our model based on what is the current damage levels versus what was predicted in our model, and we can calibrate our assumptions based on that. And we have validated our approach through lots of projects. So here, going into the methodology of our model, and based on the cases that we are given, here we're focusing on chloride-induced corrosion. So I'm not going to present on our capabilities on carbonation-induced corrosion, rather focus on chloride-induced corrosion. So we use a finite difference solution to fix second law of diffusion. So this is similar to what Mark presented earlier on Life 365. But here we have full control over the process. So we do the discretization with depth of the concrete and also with time, but we have full control to decide what are those delta X and delta T that to use. And that gives us capability to model even shallow cover. So it's the most discussion we had earlier here. So at each time step, we look at the chloride profile. So we look at how that changes with time, and we define the initiation time as a time where the chloride concentration at the depth of the bar exceeds the critical concentration, which we call the chloride threshold. And since we are performing probabilistic modeling, we describe the key input parameters with probability distributions. And our model is flexible, that we can use any probability distribution. We're not limited to normal distribution. So we often use, for example, log normal for cover distribution. We use beta distribution to define the chloride threshold for black bars, for example. And again, we rely on what is the specific conditions of the project to define those input, the distribution for this input parameter. And the results would be what is the probability of failure, or here in the case that we are discussing today, what is the probability of corrosion initiation with time. So typically I'm going to go briefly on how we define the input parameters. Typically, for example, for the cover, we rely on the design drawings to decide on the average value, and then we decide the distribution based on typical construction tolerances. Sometimes this is not defined early in the project, and we use the service life modeling to inform what is the appropriate cover thickness to use for the element that we are analyzing. For the diffusion coefficient, we like to rely on lab testing. This can be C1556, which is you test saturated samples, you expose it to sodium chloride solution for a specific exposure period. So in the standard, it's defined at least 35 days. And then you look at the chloride profile, and based on that, you estimate your diffusion coefficient. You can also use NT-build test, which is defines the chloride migration coefficient. So it's a little bit different from the diffusion coefficient, because in this test you drive voltage through your sample, and you measure what is the chloride, how far the chloride penetration got in your sample, and based on that you can define what is the chloride migration. Or you rely on data presented in the literature. So here, for example, the data is correlations that's presented in the manual for Life 365 based on extensive literature of bulk diffusion testing, and they have a correlation to define the diffusion coefficient based on the water-cement ratio. And then for exposure condition, you can rely on historical data, or even better, if there is an opportunity to test samples from adjacent structures that could give you more accurate representation to what is the exposure condition on the site. For the chloride threshold, this is dependent on the type of reinforcement you're using, if it is black bar, galvanized, epoxy coated, stainless steel. And also it depends on, it's a function of what is the cement content and supplementary cementitious material you have in your mix. So typically for our model, we define the chloride threshold based on data presented in literature, but we also keep refining that based on data that we have collected from previous projects. So we collect concrete cores and we look at the chloride concentration at the bar depth and what was the condition of the bar, and we build a database of this information that we can refer to define some of the distribution for corrosion resistant reinforcement. So here going into the modeling cases. So we have 3 cases, 3 mixed designs, and 2 types of reinforcement that we are considering. And the target initiation time is 100 years, with 90% confidence. So we discussed here that a little bit earlier and with other presentation. So we are interpreting that we need a maximum of 10% probability of corrosion initiation at 100 years. So for the diffusion coefficient, we were given results using NT build for 92, and also bulk diffusion test results C1556. And based on our extensive experience with project work, we found that NT build for 92 tend to give us conservative results relative to the diffusion coefficient. And based on that, apparent diffusion coefficient provided us with more representative values. So here we are using in all the results, and I'm going to show after, we are relying on the results from ASTM C1556. Then talking about aging factor. So the diffusion coefficient decreases with time as a concrete matures. And we describe that in our model based on the aging factor. So here the provided information that were given as part of the inputs were mainly bulk electrical conductivity testing. And so I'm showing here the results we have from that test. And it was also given to consider 8 years of hydration time. However, any electrical testing actually is affected highly by the chemistry of the core solution as well, which could potentially give you misleading results, especially with some of the supplementary cementitious material. So you have to be careful considering the lab test results when you're performing your service life analysis. So based on the bulk electrical conductivity, this was the calculated aging factor, so similar to the numbers that Brad mentioned earlier. And to give you an indication on how aging factor can affect the results, so here are 2 curves, same D28, but with different aging factor. The blue line is using an aging factor of 0.24, so and assuming a hydration time of 8 years. So you can see you're getting to a value about 0.04 with a lower aging factor. With a higher aging factor of 0.84, similar to what we are getting for the pozzolan mix here, you're getting very, very low value at 8 years. So you're getting down to 0.002. So aging factor affects the results significantly. And so it's very important to take a step back and evaluate the lab test results before using it in your model. For exposure condition, we interpret the maximum chloride concentration as the ultimate value that you would get it at the surface, and we used a buildup time of 5 years for the cases of bridge deck with the icing salt, and also for the marine splash case. So it takes 5 years until you get to those ultimate concentrations. For the submerged zone, we didn't assume any buildup times. We assumed that this value is going to be there from the beginning of exposure. For splash condition, since for the case that we're given here for marine wall with a splash exposure condition, we recognize that wetting and drying in the splash zone going to result in what we're calling here convection zone. So this would result in deeper chloride peak because in the non-saturated region near the surface, diffusion is not the main transport mechanism of the chloride anymore, and you have some capillary suction and absorption that contribute to your chloride penetration. And to consider that in our diffusion-based model, we consider transfer depth. So this is the depth until that peak of chlorides in your concrete. So this is similar to what is presented in Fib 34. And Fib 34 gives you a distribution to use for that transfer depth function. So it gives you a beta distribution with an average value of 0.35 inches. And we validated that through lots of investigation on actual marine structures. So we looked here, for example, I'm showing few profiles, but while I'm doing this work, I looked through 3 different projects that we did before, so more than 30 chloride profiles, and based on that, the Fib 34 distribution actually is a good representation of that transfer depth. However, when I looked at those profiles, there are many of them that still show diffusion-based chloride profile. So it's on the conservative side to use the Fib 34. For the bridge deck, with the icing salt and the marine wall with submerged case, so here we don't expect transfer depth. So we assume transfer depth of 0 for those cases. So here's, for example, some chloride profile from tidal zone, and same thing with chloride profiles from bridge decks. We have seen many of those, and those are typically dominated by diffusion chloride transport. So getting into the modeling results. So here I'm showing color-coded tables that shows the time until you get to 10% probability of corrosion initiation. The table on the left here shows the cases with black bars, and on the right, the enhanced bar. And we looked at what would be the results using the different mixes and the different cases here. These results here are based on the inputs that we are given. So we considered the aging factor based on the electrical conductivity testing. We considered the chloride thresholds that are given. And based on that, similar to what others have presented earlier, that black bar didn't give us 100 years of target service life. And for the cases with the control mix or the silica fume mix, and for the enhanced bar, the control mix also didn't give us 100 years, but silica fume mixes and natural pozzolan got us to the 100 years. However, if we are modeling this for a project, we might have approached some of these input parameters differently. So, for example, looking at the bridge deck, the ICER case here, and let's look closer at the aging factor. So the results I presented earlier is based on the calculated aging factor from the bulk electrical conductivity testing. However, again, because this is affected greatly by the chemistry of the pore solution, which has little to do with the chloride transport in concrete, we would prefer to rely on NC build results or ASTM C1556 at later ages. However, that doesn't, recognizing that that takes a long time and sometimes it's not feasible with new construction, we turn into the literature. So here, for example, I'm showing the value if we use the data presented in the literature and presented in Life 365 for aging factor. And Life 365, or the data actually presented in the literature and Life 365 summarize that, it assumes 25 years of hydration time. So the testing that was done to produce this data looked at chloride profiles at different ages until 25 years. And conservatively, they capped the hydration time to that value, to the 25 years. And they came up with a correlation based on the data they have seen on what would be the aging factor as a function of what is the percentage of fly ash and slag you have in your mix. And conservatively, they capped that value to 0.6. So here, if we looked at the mixed designs that we are given and use the correlation given in Life 365 to estimate the aging factor, we get lower value. And for the natural pozzolan case, it's much lower. So if we consider that this natural pozzolan performed like a fly ash, and we use that to get an aging factor based on correlation Life 365, we get 0.36, so which is much lower than 0.84 suggested by the bulk electrical conductivity testing. However, keep in mind that when we use the bulk conductivity testing, we were assuming 8 years of hydration time, but with the Life 365 values, we are assuming 25 years of hydration time. And here's a comparison of the results. So, the curve that you're looking at here is how the probability of corrosion initiation, it changes with time. And, the values in the curves and solid lines are the one with given input parameters for the session. The dotted line is when I revise the aging factor to be consistent to the assumptions presented in literature and in Life 365. And this table here provides a comparison of the two. So with the literature aging factor, we get a reduction of 12% in the predicted service life, and if we are using the control mix, it's even higher with the silica fume mix, and it's more than 50% reduction for the natural pozzolan. So this highlights the importance of thinking about how you're interpreting the lab test results, what are the appropriate assumptions for some of the input parameters. Here we're given an example of aging factor, but that could be true to other input parameters as well. Looking at the enhanced bar cases, the aging factor was not as significant with predicted service life as the cases of black bars, because especially that we are in for the mixes with silica fume and natural pozzolan, we are. I ran the analysis up to 110 years, so I didn't extend it further. Could have resulted in bigger differences if we extended the analysis period. And again, looking in more depth at another input parameter. So now let's look at the pile submerged case, and look specifically on the assumed chloride threshold in the analysis. So the provided values that were given for the session had an average of 735 ppm with a coefficient of variance of 30%. So we're assuming normal distribution. Typically what we use with CASLE is a beta distribution. This beta distribution was developed based on data that was presented in Bright's thesis in 1997, and we adopted risk categories defined in Broomfield to develop this distribution. And we recognize that the chloride threshold is affected by your mixed design, so the cement content and if you have supplementary cementitious material. And the approach that we've taken to consider that is similar to what is presented in Concrete Society TR 61. So it takes into consideration how fly ash and slag can reduce the hydroxyl ions in your concrete as they react with the hydration products and affect what we call effective cement content. And this is what we use to come up with the chloride threshold. So here is the result if we consider the given threshold and the threshold that we typically use with WJE CASLE. For the black bars, actually, that the values are not that far when you look at the average on the table on the top here for the control mix. Then the equivalent chloride the equivalent cement content used to calculate the chloride threshold gets more different when you have like silica fume and natural pozzolan. So here, comparing the two, when we're looking at the control mix, we estimated 1 year greater than the predicted service life if we're using the given threshold, but considering the short predicted service life, this is actually 7% change. With the silica fume mix, we are predicting 5% less in terms of predicted service life compared to the given threshold. For the natural pozzolan, we're not seeing much change, especially that we're looking at 110 years as our analysis period here. So in conclusion, we would like to highlight here that the accuracy of your model depends on how accurate you're representing the mechanism. So, for example, if you have splash zone, you have to consider transfer depth, and also how accurate are you representing your data, so your input data. So, how representative and accurate are your characterization of your input distribution. So here, I'm summarizing the cases that we ran. So when we looked at the aging factor, you see a big difference between the assumptions between the data that we're given as part of the input parameters for this session, and then with the aging factor presented in the literature. And the same thing with the threshold, also that provided some changes with the predicted service life. So it's very important to take a step back and look at how you're getting your input parameters and how they are representative of the actual condition, and how much changes you need to do or to consider to your modeling approach to capture all of those changes. And thank you.